In this video we will see about strain energy. So here if you see strain energy of a bar under axial load. So if we apply axial load to a bar, then we have this formula, strain energy formula, which is integration of 0 to L and over entire length. This Px is a load variation with respect to length, Px square dx divided by 2 area x and Ex. So here area E and P all are varying with respect to x. So we have to integrate it from 0 to L. So they are function of x. But if they are constant with the length, then we can simply write u is equal to p square L by 2 AE. So here P is a load, L is a length, area and Young's modulus. So this is how we have to calculate strain energy of a bar under axial load. Now you see strain energy can be calculated from half into P into delta L, change in length, load and multiplication factor half. So this is area under load versus deformation, means delta L diagram, which is gradually applied load. Now this can be also written as sigma square by 2E into volume. So if it is per unit volume, if they ask strain energy per unit volume, then simply sigma square by 2 into E. Sigma is stress, which is P divided by area, and volume is area into length. Now these all formulas are for strain energy of a bar under axial load. Now if you see strain energy of a beam under bending, then we simply have to replace this formula Px with Mx and Ae into Ei. So here this was axial rigidity, here it is flexure rigidity. Ei is flexure rigidity, A is axial rigidity. So u is equal to integration 0 to L. Mx is bending moment which we are applying on our beam with respect to x. So if it is varying with x, we have to put a function of x here, mx square dx upon 2 E into I. I is inertia of cross section, E is a Young's modulus. So if all are constant and they are not changing with x, then m square L by 2 EI. Similarly, if there is a shaft under torsion, then we have to write u is equal to integration 0 to L Tx square dx upon 2 Gj. So all are varying with x, that's why we have to keep functions. If they are constant, then T square L by 2 Gj. Gj is a torsional rigidity. So this is how we have to calculate these three formulas. We have to remember, we can directly derive from here. If they are not constant, we have to integrate from 0 to L. So these three formulas are important. Now other direct questions they asked are from prismatic bar, means the area is not changing with respect to length under its self weight. So it is hanging from the fixed support, and we have to calculate strain energy due to self weight. So it will be W square L by 6 AE. Here W is mg of the bar, means weight of the bar. So W square L by 6 AE. So after integrating it with respect to this formula with respect to total length, because at varying section in self hanging there is a varying load. So after integrating, we simply get W square L by 6 A. So we can directly use this formula. If the bar is conical, then it is W square L by 10 AE. Here W is mg of the cone, so weight of the cone we have to take, and A is area of the base of the cone. So cone is hanging from the base, and we have to calculate strain energy of this conical bar with its self weight. So it will be W square L by 10 AE. Now if we see stepped bar, so in stepped bar, if you see, there are multiple bars, and we have to individually calculate the strain energy first, u1 u2 u3. If the load is changing, if area is changing, material is changing, then we have to calculate from this formula for all these different bars, and then we simply have to add this in step bar. So that will be total energy, strain energy of this material. So that is how we have to do. Similarly, if there is a beam and if we have different lengths in beams and different varying moment, then we can simply add by calculating for different sections. For first section, second section, third section, if there is a moment variation or a material variation, we have to calculate individually, and then we can directly add them. Now if we see the shaft in pure torsion, so if there is a shaft, it is in pure torsion, torque is given, then there is indirect shear stress will be 16T by pi d cube, that will be generated inside the material. Now we have formula with tau and T. So with respect to torque, T square L by 2 Gj, that we know, this is the same formula. And with respect to tau, we have this indirect shear stress, which is tau square by 4 Gj area into length. This is a volume, area into length. and tau square by 4gj. G is a modulus of rigidity. So it is in pure torsion. The torsion load is given in this, so indirect shear stress is generated. But if we give direct shear stress in our material, like here, there is a block, this black color box is there, and it's fixed on this bottom surface. If we pull it by load P, then there will be deformation like this green color. So there is some angle which is deformation is there, which is a uh, shear shear strain. And now, to calculate shear stress in a block is tau s. So that is a direct shear stress. So this is not strain, this is a shear strain in a block u. So shear strain in a block u will be tau s square by 2g into area into length. So here 4 is there, here 2 is there. That is the basic difference between these two. This is indirect shear stress, this is direct shear stress. So if you apply direct shear stress, then shear strain in block will be, so total strain energy will be q is equal to tau s square a into L divided by 2 into g. So this is two different cases. So we have to remember these two cases for shear stresses. So this was it for this video, and see you in the next video. Thank you guys for watching this video.